Good evening. Here we are once again. Man, this is a little bit later than the other one. That's okay. It took me a bit longer to get my notes together for this, so we'll see if I can get through all three of them tonight. If not, I'll record section number 3 of these videos tomorrow morning. Anyway, so for part 2 of the lesson number 2, I would like to do a few things. This is going to be over sections 2.5 and 2.6 in the textbook, and our learning objectives for this portion of the lecture are as follows. First, we wish to sort of define atmospheric pressure and gauge pressure, kind of a review from some of the things we saw in the first lecture a week ago. Second, we wish to illustrate the effects of pressure in real life. And third, so sort of a continuation of that discussion. And finally, discuss some tools that exist for measuring pressure, barometers, manometers, etc. All right, so let us review gauge versus absolute pressure. Gauge versus absolute pressure. So let's look at this. Gauge versus absolute pressure. So gauge versus absolute pressure. All right, again, gauge pressure is the pressure relative to the atmosphere. Not cage pressure, gauge pressure is defined as the pressure relative to the atmosphere. So it's always measured in relation to atmospheric pressure. It can be less than atmospheric pressure or greater than atmospheric pressure. Relative to atmosphere. Or relative to atmospheric pressure. Relative to atmospheric pressure. And then atmospheric pressure, where does that originate from? Again, that originates from the column of air above a point in the atmosphere. So again, atmospheric pressure. Where does this originate from? Just as a review from previous discussions, if we had a small 1 centimeter square piece of ground at sea level, and we looked at the column of air above it all the way to the top of the atmosphere. Now it's difficult to define exactly where the top of the atmosphere is, because it obviously doesn't just end at a wall. It sort of peters out and gets thinner and thinner as you get higher and higher. But let's just say 200 kilometers high would be a good point where you're pretty much in hard vacuum. So this is the top of atmosphere. Top of the atmosphere. And as we go up, pressure decreases, but it won't be a linear decrease. It'll be more than a linear decrease, and that is because the atmosphere is a compressible gas. We're not talking like water, where we assume it to be incompressible. The atmosphere is compressible. It's made of air. So what that means is our rho, our density changes. The density is lower is much higher near the surface and lower up top. So it's not going to decrease linearly, but it is going to decrease. It's actually going to decrease greater than linearly in some sort of power or logarithmic relationship. And again, this is 200 kilometers here, from top to bottom, approximately, of course. And the area of the cylinder, let's just say this area of the cylinder is 100 centimeters squared, or 1 centimeter squared. And if we were to if we could somehow measure this directly, we would find that there is a mass of about 1 kilogram, or a weight of 10 newtons. Hey, that's not that much, right? I mean, what's a kilogram? Kilograms is a couple pounds. It's not a big deal, right? Well, look at the area. That's on 1 centimeter, on a single 1 centimeter square piece of area, and that is applied to every single square centimeter on an object. So we can see that air pressure can actually be quite large, or actually is quite large. So not only can be, it is quite large. So let's talk a bit about units. So P atmosphere is equal to about 1 kilogram per centimeter squared, which is approximately equal to 10 newtons per centimeter squared, which is approximately equal to 10 to the 5th pascals. Or if I were to use more advanced, or not more advanced, more accurate measurements, a little less rough, I would say that 1 atmosphere is 101 kilopascals, or the atmospheric pressure is 101 kilopascals, or simply 1 atmosphere. So let's talk about this a bit. Make sure, and we are good. So let's talk about some implications of this. So let's think about this. Suppose the following. So I'm just going to talk, in the next few slides, I'm just going to discuss some of the implications of atmospheric and gauge pressure. Suppose we consider, so what if I hold out my hand and think about what forces are on my hand? In fact, do this at home. Hold your hand out horizontally and look at and consider this as we talk about this. So suppose we consider the human hand, our hand, and it has width approximately 150 square centimeters of area, surface area. Surface area. So the force perpendicular to our hand is 10 newtons per square centimeter due to the air above, or if we multiply by 150, it's going to be 150 kilograms, or 1,500 newtons pushing down. This is an immense amount of force. Think about that. 150 kilograms, that's over 300 pounds in English units. So imagine a 300-pound weight sitting on the palm of your hand, and you would feel that. In fact, if you were, unless you were exceptionally strong, there's no way you'd be able to hold that out on a single hand. So how is that? So that's the question. Why can't we feel this? There is clearly this immense force pushing down on our hand, but why don't we feel it? So why can't we feel this? This is the question. Why can't we feel this immense force? Well, the answer here is because of Pascal's law. If you remember Pascal's law from the previous portion of this lecture, part 1, we saw that that pressure is going to be the same in all directions. So pressure is the same in all directions. In all directions at a point. And my hand is the height of my hand, or any hand really, is small relative to the height of the atmosphere. So it's going to be, there's not going to be that much increase in pressure. Now yes, we could actually reason that the pressure is probably slightly lower at the top of my hand than at the bottom of my hand, but it's small enough to not be important. Pressure is same in all directions at a point. So we have 150 kilograms of mass in all directions. Of mass in all directions, or effective mass in all directions. And again, this is Pascal's law. This is simply Pascal's law. Okay, so let us look at another case. What if I were to look at the case of a submarine? What kind of forces act on a submarine? So, say we have a submarine. It's under the water surface, completely enveloped in water. Here's the water surface. And here's the submarine down, and I'm going to say it's for this particular submarine, I'm going to say it's at a depth of 900 meters. It's rather deep for a submarine, but that's okay. 900 meters. And let's look at the forces or the pressures that are applied here. So inside the submarine, I'm going to have 1 atmosphere. You know what? I'm going to redraw this. I want to be able to have enough room to show this. Maybe this will work better. So pushing outward, I'm going to have the gas inside the submarine, which for our purposes, let's assume it's exactly at 1 atmosphere. Now you might be able to make things easier by pressurizing it, but let's just say this is at 1 atmosphere. And then the outside, the water would be pushing in with another much greater pressure. And this pressure, P, is going to be equal to, well, we can find it from the equation we've previously derived. P is going to be equal to 900 meters times gallon water, well, times 10 kilonewtons per meter cubed, plus 1 atmosphere. That is the atmospheric pressure pushing down the water, plus the pressure from depth of the water itself. And this comes to approximately 91 atmospheres, absolute pressure. What about gauge pressure? So let's think about that. Rule of thumb. So again, so let's back up a bit. There's a good rule of thumb for depth that you might want to keep in mind. So if you're working through problems on homework or on an exam, you might want to keep this in mind. For every 10 meters of depth, for water, of course, you gain approximately 1 atmosphere pressure. Approximately. Or about 101, or about 100 kilopascals. Okay. So let's talk about the forces on here. If the sub has area, if sub area is approximately, let's say it's 900 square meters, which isn't unreasonable for a submarine, this would translate to a force, a simple multiplying pressure times area, of 819 meganewtons, absolute. And if you don't have any idea any conception of what a meganewton is, it's 322 times 10 to the 6 pounds of total force. Now, what if we look at gauge pressure? What about if only 1 atmosphere inside? So this won't actually determine the stress in the material of the sub, in the walls of the sub, the forces in the walls of the sub. The atmosphere inside will be able to resist some of that. However, if it's only at 1 atmosphere, if only at 1 atmosphere inside, then this means that there is a 90 atmosphere difference. There's going to be a 90 atmospheric pressure, or 90 atmospheres of pressure difference between the outside and the inside. And the way this is going to stay balanced is that the hull is going to resist it through simple compressive stress of the hull. So you're going to need a very strong hull. Submarines are, especially like military submarines and things like that, are incredibly engineered. The welds on them are incredibly precise. The amount of force they have to take is just astronomical. So submarine hull design is not something to be taken lightly. Okay, so next case, let us consider a soda can. What happens if I look at a soda can? Let's look at a soda can under a few cases. Let's consider a common soda can. Common soda can. So let's consider this under two cases. Let's say one I'm going to open to the atmosphere, and another I am going to pump all of the air out somehow. Let's say this one, and I cannot draw something that looks like a soda can, I know, just say they look like cylinders, but oh well. This one is open to atmosphere. This one is, we're going to remove the air inside and see what happens. Well, as you can probably see, this isn't going to go well for the can on the right. This one here is 1 atmosphere inside, 1 atmosphere outside. In balance, the can doesn't really have to take any pressure forces. In balance, here we have 1 atmosphere outside, 0 inside, and now the can will have to try to resist all of the forces, the full force of the atmosphere with nothing to balance it. So what's going to happen is that the can will crush. The can crushes. So what if I were to look at a scuba diver next? So this is another instance of another application of pressure. Scuba diving. Consider scuba diving. So let's say you were to try, let's think about, or what I want to look at is, what if you were to try to breathe 1 atmosphere pressure air while deep under the water? So you sometimes do that, for example, snorkeling, but that's basically, you're floating right at the surface. The only point of snorkeling is that you can look downward, have your eyes under the water, and that makes things a little bit easy. That makes it a lot easier to see things under the water. But let's say you were actually to try to get a really long snorkel. Like let's say you had a 10-meter long snorkel. Let's think about what that would look like. So say you have a person. I'm going to draw them as a stick figure. Here. And we're going to have a 10-meter long snorkel. A ridiculously long snorkel. And somehow we decide, you know what, we're going to, this is a tube, and we'll make this out of steel or something, so it's not going to be made out of like simple flexible plastic like most snorkels are. We'll make it out of steel, just so we know that the water pressure will collapse the tube. It's going to stay all the way through. It's going to stay open all the way. And this is 10 meters. So, let's see. This is going to be at 1 atmosphere. And through this, I'm going to make it, through this tube, I am going to try to breathe 1 atmosphere air while under 10 meters of water. Let's see what happens. So, if your lungs have 1 atmosphere of pressure. Well, I chose 10 meters because this is about, this will produce about 1 atmosphere of water pressure. But 2 atmospheres on your body well, this will result in 1 atmosphere net pressure of pressure on your lungs, on the outside. On your lungs. Hey. Again, where this is coming from, where the 2 atmospheres is coming from, is P equals 1 atmosphere plus 1 atmosphere equals 2 atmosphere. But each of these, this is the air and this is the water. This is the air above and this is the pressure from the water. In this case, they're the same, to make the math simple. Now, if area, so let's find force, let's look at forces. If area of your chest let's say it's approximately 1,000 centimeters squared. I'm doing rough numbers here just to illustrate how this would work. It is like having having 1,000 kilogram. It's like having 1,000 kilogram of mass on lying on chest and on back, on chest, on back, and on sides. Squeezing you to death, quite literally, if you were to try to maintain 1 atmosphere of pressure in your lungs. If you tried to do this and you somehow kept a good seal on there and kept 1 atmosphere of pressure on there, it would collapse your lungs. So what divers actually do, for those of you who've done some sort of scuba diving, you'll know that you use a pressurized air tank. The 10-meter long tube would be analogous to trying to breathe with a tank of 1 atmosphere pressurized air. That's not going to work. There's going to be an immense pressure differential. So instead, divers used pressurized air. Now they get into it gets a bit more complicated when you start talking about partial pressures of various gases and all this kind of stuff. But we're not going to worry about that, so that's okay. Inappropriate dive mixes and all that fun stuff. So, again, let's talk about absolute pressure. This is a review from previously, but I'm going to use this in my discussion of barometers and manometers to follow, so that's why I'm doing it. Absolute pressure. Well, absolute pressure is again relative to absolute zero, or to a vacuum, or a perfect vacuum. Relative to absolute zero, and we remember that P absolute is equal to P atmospheric plus P gauge. And let's review how this will work with a column of fluid. So P absolute equals P atmospheric plus P gauge. And if I have a column of fluid, or just a depth of fluid, with a surface here, and I'm going to have points 1 and 2, so just some point 1 at the surface, at a free surface, 1 and 2 separated by height h, with a, I like using green for my dimensions, separated by height h. Well, I'll have the following pressures. Well, P1 at point 1, it's going to be zero gauge pressure, or P atmospheric for absolute pressure. Down here at 2, P2 is going to be P1 plus gamma H in general terms, or P2 is going to be equal to gamma H if I'm talking gauge pressure, or P2 is equal to P atmospheric plus gamma H if I'm talking absolute pressure. So this is the gamma H, gamma times H, specific weight times H. This is going to be my gauge pressure, and this is going to be my absolute pressure. And if I want to remember what suction is, I don't know if I've mentioned that before. What is suction? Well, suction, say like in a common vacuum cleaner or something like that, suction is negative gauge pressure. Absolute pressure can never be negative. You can never have absolute pressure being negative. However, you can have negative gauge pressure. Negative gauge pressure In other words, below atmospheric. Below atmospheric pressure. Suction, or the illusion of suction, or what we describe as suction, will be generated when the gauge pressure in a system is less than atmospheric pressure. Okay, so next I want to move on to talk about, so I'm going to use those tools as I move through the lecture. Next I'm going to move on to describing some pressure measuring devices. Make sure everything's still rolling, and yes it is. Okay. So let us discuss some pressure measuring devices. Well, the first one is going to be the common barometer. The common barometer. Now, nowadays we tend to use more electronic means to measure pressure, but these are sort of some classic devices used to measure pressure, and we like to talk about them when we teach fluid mechanics because they help us understand principles of Pascal's law and pressure changing with height, that sort of thing. So again, we now know about atmospheric pressure, but how do you actually measure atmospheric pressure? So we know about atmospheric pressure, but we want to know, how do you actually measure this thing? So one way to do it is to use a barometer. There's a whole bunch of ways to do this, but one common way, at least for measuring atmospheric pressure, is to use a barometer. So a barometer is a device to measure atmospheric pressure. What it consists of is a simple barometer is going to consist of a tray or a vessel or a pan or something like that, filled with, commonly mercury, with a tube in the middle, a high tube elevated in the middle. And then there is going to be a fluid. Now, you don't have to use mercury, but although it is most commonly mercury, and we will discuss why shortly. And there's going to be a free surface here. A free surface here, and then just a surface here. Free surface generally means exposed to atmosphere. Okay. So I'm going to have two pressures I want to consider. I'm going to have, I'm going to call this P1 and P2. This portion of the tube has been evacuated. The air has been pumped out of here. So this is basically near vacuum. P1, the absolute pressure is approximately 0. The only pressure here is the vapor pressure of the fluid. If you need to review what vapor pressure is, consult your elementary chemistry book. But we don't need to worry about that. It's so small, especially for mercury, it's so small it scarcely can be said to exist at all. For our purposes, it might as well be 0. P2 is going to be P atmospheric. So what's happening here is that there is a atmosphere. So this portion of the fluid is exposed to the atmosphere, and P atmospheric is pushing down on the free surface here. But yet we notice this change in height, this difference in height. The fluid is actually forced upward a certain height h. And at first this may seem like magic. Like, why is this fluid? We're used to fluids in balance keeping their own level. Like if this were open to the atmosphere, if I cut this off and let air flow in, the atmosphere flow in, this would return to a level state. But because this is a vacuum, that's not going to happen. Seemingly by magic, and I'm just showing that this has a gamma Hg, gamma mercury. So the question is, what is keeping this fluid elevated? That is the question. Q, question. What is keeping the fluid elevated? Is it magic? Is it witchcraft? Is someone casting a magic spell on this thing? No, clearly not. Keeping fluid in the pipe. And the answer is the atmospheric pressure. And the answer is the atmospheric pressure. The atmospheric, the P atmospheric. That is what's keeping this thing in balance. So I could say P atmospheric minus P1, I'm just comparing the height from Z1 to Z2, or Z2 to Z1 actually, is equal to gamma. So all I'm doing is running through this equation, well, our atmospheric equation, just our increase in pressure with height equation from the previous lecture. Z2 minus Z1 here, or B atmospheric is equal to gamma H, gamma time. Now that's not gamma subscript H, again, that is gamma times H. Here, gamma times H. Now, we typically express, oh, actually, let me go back here, do this one here. Just a few notes. Let's see. We typically express pressure in height as height, either in inches or millimeters. So, for example, you may have heard, you probably have heard, I hope you've heard. Example, you might hear the atmospheric pressure reported as 759 millimeters of mercury. That is referring to how high the atmosphere is currently capable of pushing a column of mercury. So, again, this is going to be 759 millimeters over 1,000 millimeters per meter times the density of mercury is, well, the specific weight of mercury is 133 kilonewtons per cubic meter, which is going to be 101 kilopascals. So, atmospheric pressure. So then a question I have is, I have one other fun question. What if we used something other than mercury? What if we used a column of, say, water? Used a column of water. How tall would the column have to be? The column have to be. How tall would the column have to be? Well, let's see. So we know that the gamma of Hg is going to be 133 kilonewtons per cubic meter. And so that produces a height of 759 millimeters to get an atmospheric pressure equal to 101 kilopascals. Well, the gamma of water is 9.81 kilonewtons per cubic meter, and so 101 kilopascals is going to be equal to the same pressure. I'm just doing this in terms of gauge pressure, or actually absolute pressure in this case. 9.81 kilonewtons per cubic meter times our height h, and I get that h is equal to 10.29 meters, or 10,290 centimeters. So need a tube approximately 14 times as high. And this is why in the olden days, where they actually frequently used barometers like this, you wouldn't see water manometers, although I suppose you could build one. Another problem with that is that the the water will tend to evaporate as high, 14 times as high. The water, if you use water, it will tend to evaporate and go off into the atmosphere, so you need to periodically refill it. Mercury, maybe a little bit, but it'll generally be a great deal more stable than a water manometer, although I don't know if anyone ever used water manometers, except maybe some bored physics or chemistry teacher simply illustrating the point that it could be done. For example, if you were, think about this, a 10-meter high barometer, that's 2.5-story tile barometer, you're going to need to build a building around this manometer. Sorry, not manometer, barometer. You're going to need to design your building around this barometer. I was getting ahead of myself. Now let's actually talk about manometers. So what is a manometer? Well, first let's talk about the simplest kind, a straight tube manometer. Manometer Well, a manometer is a device. I don't know if I can change my pen here. It is a device that measures pressure. In vertical or inclined tubes. Inclined tubes. Alright. So you have something like this. So say we have a pressurized system like a boiler or something. And I want to see what kind of pressure this thing is under. So this would work good for like an old-timey steam boiler or something. And it's going to have, the same fluid is going to be in the column and inside the pressure vessel. So I have, say, a gamma here, and this is going to be the same throughout, and whatever fluid is in the vessel is going to be right up to a free surface here. And then I have a point A, let's just look it up, consider a point A at the bottom of the bottom elevation of the tube, and the height here, the pressure in the fluid is elevating this column a height of h. So then, if I work through this, PA minus P1, well this is point 1 here, PA minus P1 equals gamma times ZA, ZA minus Z1. Now, usually I'm going to be talking about in terms of gauge pressure, so I can just say this is equal to 0, and then I'll end up with, let's see, then I will simply end up with the following equation. I will get PA is equal to gamma H, and that is the gauge pressure for a straight tube manometer. If you want it, they're nice and simple. All you need to know is, if you want to know the pressure, just multiply the height times the gamma of the fluid. This is the gauge pressure for a straight tube manometer. However, this system has some severe disadvantages, which is why you don't often see it. Well, nowadays everything's digital, but anyway, even in the olden days you didn't tend to see this. Disadvantages. Well, let's see. One, you need small pressures. The system needs to be on relatively small pressures. Needs small pressures because the tube needs to be short, relatively short. Pressures, so tube can be short. You know, in terms of like an instrument that you might read at a plant or something like that, it's not going to do you any good if the tube is 10 meters long. It's not going to be something you can reliably and accurately read. Notice, because this is limited to whatever fluid you are using. I mean, sure, if you happen to have a vat of boiling mercury for some insane reason, you could keep this to a reasonable height, but not many people really need vats of boiling mercury, so that's probably not something you need to worry about. But if you have, say, a boiler, well, if the pressure can't really be that high, otherwise this won't be able to really read it because the tube will be way too long. Other problems, the pressure must be larger than atmospheric. If it isn't, or else air can be pushed back into the system, which can be very bad, depending on what process you're using. But generally it's a bad thing if air comes into a vessel like that. Three, notice this only works for liquid processes. I need a container of pressurized fluid because there's no, what is inside the container is going to be directly in the tube. So this will only work for, can only measure pressure in liquids. Pressures in liquids, not gases. In liquids, not gases. So instead, let us look at the Tube manometer. Now, you're watching this video on YouTube, but that's a different thing entirely. So let's talk about a letter U, Tube manometer. So instead of simply having a straight tube, I'm going to use a bent tube, and I'm going to fill that bent tube up with a certain fluid. So let's say I have a vessel, and then I go and attach a bent tube to it, and this will create some interesting properties. So, if the pressure inside this gas, let's say this gas is going to have a certain pressure, but it's also going to have a certain gamma. So I'm going to say gamma gas, and I'm going to label a whole bunch of points. So I'm going to let this be point A. Then at the start of where the tube starts to dip down, I'm going to call this point 1. I'm going to call where the gas ends as point 2. I'm going to call the bottom of the tube point 3. I'm going to say the point that is level with the end of the gas is point 4, and the top of the fluid is going to be point 5. And what do I mean by this? Well, this gas, there's a gas here, and it is forcing this. There's a fluid in this tube, but not all the way. Just imagine it started out level. It started out, say, like right here. But when this pressurized gas hit it, it forced it to become imbalanced. Well, not imbalanced, but one side higher than the other. So this is our surface here at point 5. So 5 is right at the surface of the fluid. So this thing is now, because the gas is pressurized, it is pushing harder on this than the atmospheric pressure, so this is forcing this down and forcing it up against atmospheric pressure. And the density of this one is going to be this, I'm going to say gamma GF. This doesn't stand for girlfriend, that stands for gauge fluid. Isn't that what most people use for that abbreviation? That's what I use for that abbreviation, because I'm very cool. Anyway, so I'm going to apply the formula. I'm going to apply the formula, the hydrostatic pressure formula. And I'm going to do this a series of times, the hydrostatic pressure formula. And again, that formula that I'm going to use repeatedly to analyze this thing from piece to piece is P2 in general, not these specific points, but if you have two different points, P1 plus gamma times Z2 minus Z1. Oh, and I need to label some heights. I think we can't get that without that. We won't be able to work with this without our heights. And so let's just say, for our purposes, this is H1. I know they don't match up exactly with the numbers, but whatever. This is H2, and I'm going to let this here be H3. This is H3. Oh. H3. And of course, our coordinate system, I'm going to measure it. I'm going to measure Z. I'm declaring the 0 line, the peak of the gauge fluid, and it's measured downward with positive Z. Now, something to keep in mind as I set up the following equations. Recall when we go down through a fluid, we add pressure. When we go up through a fluid, we subtract pressure. So we're going to do that repeatedly. So essentially, I'm just going to work bit by bit through the whole thing. I'm going to start here and just move from left to right, from point 1 to point 5, from point A to point 5, and analyze this. And notice the pressure at A in the gas is going to push directly against the gauge fluid here. So I'm going to do a series of 5 steps, and you know that you don't necessarily always need to do this, but I'm just doing this very thoroughly and methodically to show how this works. So 1, calculate pressure at 1, pressure at point 1 based on, so I'm not going to have numbers here, I'm just going to do this relatively, just in terms of numbers. Well, I know that, again, based off of our standard formula, P1 is going to be PA plus gamma times Z1 minus ZA. However, this change in height is going to be 0. This change in height is going to be 0 because we see that the heights are the same here. So this will lead us to, rather intuitively, that P1 is simply equal to PA. Not really that surprising. P1 is equal to PA. Here. Next, if I want to calculate pressure at 2 based on P1. So 2, calculate pressure at 2 based on pressure at 1. At 1. So P2 is equal to P1 plus the gamma of the gas times Z2 minus Z1. And this will lead us to that, however, sorry, I need to show you my next step. However, I need to keep in mind here, or not to keep in mind, just be aware, or I can realize, whatever verb I want to choose, that gamma of gas is effectively 0. I mean, it's not actually 0, but it's so small, we can say it's approximately 0. Compared to the fluid, it might as well be 0. So from that, we will get that P2 equals P1 equals PA. We really won't start getting changes in the pressure until we start going through the gauge fluid. It could be water, it could be mercury, it could be anything we like, but it's going to be way more dense than air. So 3, calculate pressure at 3. Pressure at 3 based on P2, or based on the pressure at 2. Based on P2. So P3 is going to be equal to P2 plus gamma GF, the gamma of the gauge fluid, times Z3 minus Z2. And then, therefore, we can get that P3 is equal to, simply substituting in, if I realize that P2 is equal to PA, and I'm going to try to keep this in terms of PA because that's really what I'm kind of trying to find. PA plus gamma GF and Z3 minus Z2, if we notice here, Z3 minus Z2 is going to be this H2. Z3 will actually be a greater number than Z2 because we notice that Z is 0 and positive downward. PA plus gamma GF times H2. Here, this H2. Next, so that's something. Let me actually go ahead and box these because these are kind of nice pieces along the way. Box this and box this. Okay. Step 4 of 5. 4. Calculate P4 given P3. We have P3 figured out. Let's find P4. So P4 then, P4 is equal to P3 plus gamma GF times Z4 minus Z3. However, Z4 is actually going to be less than Z3, so this is going to be a negative number. I can realize that this is Z4 minus Z3 is basically going to be negative H2. Negative H2 here. Z4 to Z3 is negative H2. So then, P4 is equal to, now I'm going to replace P3 with this P3. PA, so I'm going to substitute this expression for P3 in here. PA plus gamma GF times H2, and then plus gamma GF times negative H2. Now, if I have a plus gamma GF H2 minus gamma GF H2, these two terms are simply going to cancel out. These two terms will simply cancel out. So this one's going to go away, and this one's going to go away. 0, 0, cancel out. Actually, I don't want to say they're 0. They're not 0, but they're going to cancel out. This one will cancel out this one, and vice versa. So this will lead us to P4 is equal to PA. In other words, note, P4 and P2, these are exactly the same. They're at the same level, same fluid between them, constant gamma. They should have the same pressure. And since the pressure at here is simply the pressure of the gas, the pressure at point A, then the pressure at point 4 is simply the pressure of the gas. Anytime you go across a tube at constant elevation through the same fluid, now if we had one fluid here and another fluid here, like two fluids joined together in the middle somewhere, then you could get some differences. But as long as they're the same fluid, the pressure on either side at the same elevation should be the same. And so let me box that here. And then finally, let me just go ahead and, I guess I can try to squeeze it into this slide. 5, actually I'm going to go ahead and move it over here. 5, calculate P5 given P4. Well, P5 then. P5 equals P4 plus gamma GF times Z5 minus Z4. And then, let's see, P5 is equal to PA plus gamma GF. Now, let's see, Z5 minus Z4, this is just negative H3 from our original diagram. And as long as we're concerned with gauge pressure, as long as we're content with gauge pressure, P5 must be 0. So we'll get the final result that PA is simply equal to gamma GF H3. PA is just gamma GF times H3. Gamma GF times H3. So it's the gamma. So it's basically, to find the pressure here, all you need to do is multiply by the difference in height between the tubes, the difference in height between the columns times the gamma of the gauge fluid, or fluid you're using. And this is what's really useful. You can simply look at the difference in height and multiply by gamma. And so you can use this for a liquid, you can use this for a gas, and because it's based on the gamma of the gauge fluid rather than the gamma of the fluid here, you can use a very dense fluid that allows for a short column, such as mercury. And that's the real value of the U-tube manometer. Finally, I just want to work through one single example problem and sort of bring this all together. And then this portion of the lecture will be finished. And so I'll just do a quick example here. So I am told the following. I am told that I have air at a certain pressure, and that this has produced a column in a U-tube manometer that exhibits the following behavior. So here I have air at a certain pressure, and then I have a tube here, a U-tube. Here. And so let me show you here. This is going to be air at a certain PA. Not atmospheric pressure, just some PA. And then let's say I have 2 points. Let me show you the levels here. This one is actually going to be lower. This one's actually going to be higher than this one. So let's turn it on its head from last time, or from the previous example. Although that was an example without numbers, it was still an example. So I'm going to let this, I'm told that the height from the bottom of the tube, or mainly the middle of the bottom of the tube, the center line of the tube's bottom, is, let's see here, this is here, well this is 5 feet, and this is 2 feet. And let me label my points then. I'm going to call this, this is point 1. At the same elevation as, basically at the point where the tube starts to go down. This is point 2, point 3, and point 4. And I'm also told that this is, so all of this is given. And I'm told that the fluid is water, so gamma water is 62.4 pounds per cubic foot. And I am asked to find PA, the pressure inside this vessel. So solution. Well, I'm just going to go point by point by point. And then I'm going to show a shortcut method that you can probably maybe already guess. 1, let's go from PA to point 1. PA to point 1 here. Well, P1 is going to be equal to PA plus gamma air times ZA minus Z1. However, there is no difference in height between the air and the point 1, between the opening anyway. So I'm just going to go ahead and say this is 0, and this will lead us, unsurprisingly, to P1 is just equal to the pressure inside the vessel. 2, for step 2, I'm going to go from 1 to 2. 2, I will go from 1 to 2. And I will say that, let's see, P2 is equal to P1 plus gamma air times Z2 minus Z1. However, I can essentially say that gamma air is 0. It basically has a density of 0 compared to the density of water anyway. So I can say this is 0, so this whole term goes away. So therefore I can get the relationship that P2 is equal to P1 is equal to PA. Then step 3. Step 3, I want to go from 2 to 3. 2 to 3. So I'm going to now say, now I actually do need to have some non-zero quantities. P3 is going to be equal to P2 plus gamma of water times Z3 minus Z2. And P3 then is equal to, I know that P2 is PA, so PA plus 62.4 pounds per cubic foot times Z3 minus Z2, which is going to be a difference of 5 feet. And that's P3. And this is going to lead us to that P3 is simply PA plus 312 pounds per square foot, PSF. Next, step 4, I'll go from 3 to 4. 4, I will go from 3 to 4. And P4 is, actually this is going to be our final step, is going to be P3 plus gamma of water times Z4 minus Z2. However, Z4 minus Z2, Z4 minus Z3, sorry about that. Z4 minus Z3, I'm getting a little ahead of myself. Z4 minus Z3, this here is negative 2 feet. Just, again, this, going Z downward is positive. And so then, also, there's another thing to keep in mind is we're going to be working with gauge pressure. So this is 0. 0 because of gauge. And then I can say 0. I'm going to get rid of P3 and put in, I'm going to replace P3 with PA plus 312. PA plus 312 PSF here, plus 62.4, that looks really bad, 62.4 pounds per cubic foot times negative 2 feet here. And this will come to PA is equal to negative 187.2 pounds per square foot. And that'll be the answer. So how can it be negative? Well, what we saw earlier is that a negative pressure is suction. So this is actually, this system is at a lower this gas is at a lower atmospheric pressure. Sorry, it's at a lower pressure than the atmosphere. So it's actually sort of sucking. It's generating a suction, and that will cause this gauge fluid to be raised up towards the lower pressure region. Now there is a shortcut I could take. I could actually go directly from P4 to P2. There's no reason I can't do that. You don't need to go step by step by step. As long as we believe in math, there's no reason we can't just go directly from 2 to 4. So, as long as it's the same fluid, we would need to break it up into pieces if it was more than one fluid. But here it is one fluid, so we're fine. Equals P2. So P4 is equal to P2 plus gamma of water times Z4 minus Z2. And then replacing P2 with PA, 0 equals PA plus 62.4 pounds per cubic foot times a difference in height of negative 3 feet, again keeping minor sign convention. And finally, PA is equal to negative 187.2 pounds per square foot. Here. Negative 187.2 pounds per square foot. And that is our final result. So that's the last example for tonight. I think that'll do it. This has gone on long enough for here. I still have a third portion of the lecture to record, but I think I'm going to record and upload that tomorrow morning, just because it's already 10:30 here. So I think I'm going to take a break, get some shut-eye, and record this again. Finish this up tomorrow morning. And as always, thank you.